Welcome to AI Paper Podcasts. We're diving into the latest AI research papers, and today it's all about insights into DeepSeek V3, scaling challenges and reflections on hardware for AI architectures.
Yeah, this is a fascinating one.
So for a quick overview, DeepSeek V3, trained on, get this, 2048 NVIDIA H800 GPUs. It really digs into the big LLM scaling problems. It's like, memory, compute, bandwidth.
Right, and they have some neat innovations. Multi-head latent attention, MLA, for memory.
And a mixture of experts approach, MOE, that's hardware aware.
Plus, using FP8 for training, which is pretty cutting edge, and this multi-plane network topology to handle the massive scale.
What's really cool is how it points towards future hardware, like needing better low-precision support and these converged scale-up, scale-out systems.
Definitely gives you food for thought. So yeah, today we're unpacking those hardware insights.
Exactly. It's amazing how fast things are moving, isn't it? We see models like GPT-4o, Llama 3, Claude 3.5 Sonnet. The list goes on.
And DeepSeek V3 itself, of course. Bigger models generally mean better performance. That trend holds.
But yeah, the flip side is inference efficiency, especially for long contexts or complex reasoning tasks. Think OpenAI's O1, DeepSeek R1.
Those models really push the hardware, and just the sheer cost of training these behemoths is, well, significant.
So this paper isn't just about DeepSeek V3's architecture per se.
No, it's more a case study in hardware-software co-design, how they looked at the hardware constraints, those H800s, and built the model around them for performance and cost efficiency.
Right. We won't walk through every single diagram. The technical report has all that.
Our mission today is really to pull out the key learnings about that hardware model interplay.
How did the H800 specifics, the networking, shape the model? And crucially, what can we AI researchers and ML engineers take away for thinking about next-gen AI hardware?
We want to give you actionable insights, things you can actually think about in your own work.
Okay, so the paper frames it around three core challenges, right? Memory, cost, and speed.
Pretty much the trifecta for anyone scaling LLMs. And DeepSeek's whole philosophy seems to be hardware-aware scaling, building on their V2 work with MLA and DeepSeek Mo.
Let's start with memory efficiency. Feels like a constant struggle.
Oh, definitely. The paper hits you with that stat. LLM memory needs growing like 1,000% a year.
While HBM speeds are only growing, what, less than 50%?
Yeah, that gap is stark. It really forces you to optimize the model itself right at the source.
So their first weapon is low-precision FP8.
Exactly. Using FP8 instead of, say, BF16 for the weights literally cuts that memory footprint in half. A direct hit on the AI memory wall.
But they didn't stop there. The KV cache was another big target.
Yes, the KV cache. Critical for smooth conversations, but it causes its own headaches.
Right, it stores the keys and values so you don't recompute everything.
But it shifts the bottleneck. You go from compute-bound matrix multiplies, GEMM, to being bound by memory speed for vector multiplies, GEMV.
Like having a fast CPU waiting on a slow disk.
Exactly. Your compute-to-memory ratio gets worse. So, their answer is multi-head latent attention MLA.
Okay, how does MLA work?
The core idea is clever. Compress the KV states from all the attention heads into a much smaller latent vector using a trained projection.
So instead of caching the full, potentially huge KV state,
you just cache this compact latent vector during inference. The memory savings are pretty significant.
They had a table, right, comparing it.
Yeah. DeepSeek V3 with MLA is down to 70 KB per token. Compare that to Qwen 2.5 at 327 KB or Llama 3.1 at 516 KB.
Wow, that's a huge difference. Much better than just GQA.
Seems so. GQA, grouped query attention, helps, but MLA takes the compression further. They do mention other techniques too, like windowed KV or quantized compression.
But MLA looks like the star here for memory savings.
For sure. Though they also look ahead, acknowledging that even with MLA, the basic quadratic complexity of transformers is still an issue for really long sequences.
So they mentioned things like Mamba 2, lightning attention, linear time stuff.
Yeah, and sparse attention. Those are potential future directions for handling extreme context lengths.
Okay, let's shift gears to cost effectiveness.
Yeah.
That brings us to mixture of experts, MOE. DeepSeek Mo is their flavor.
Right. And the big win for MOE, cost-wise, is reducing the training compute.
How does that work exactly? Fewer active parameters.
Precisely. You have a massive total parameter count. DeepSeek V3 has 671 billion, but for any given token, only a small fraction, maybe 37 billion, are actually activated and doing work.
Compared to a dense model like Llama 3.1405B, where all 405 billion params fire for every token.
Exactly. You get the capacity of a huge model, but the per token compute cost during training stays manageable.
The GFLOPs token numbers were striking. DeepSeek V3 MOE at 250.
Versus nearly 2,500 for the big llama-dense model. It's an order of magnitude less compute.
That's huge for training budgets.
And the benefits carry over to inference, too, especially for single requests. Lower active parameters mean lower memory and compute needs then as well.
They mentioned DeepSeek V2 running fast, even on PC-level AI chips.
Yeah, nearly 20 tokens per second on an AI SoC. Dense models of similar size would struggle to hit that.
Running the full V3 model on a $10 server with K-transformers. That's impressive.
It really makes MOE attractive for personal agents or on-prem deployments where you don't have infinite cloud resources.
Makes sense. So cost sorted? What about raw speed, increasing inference throughput?
Okay, speed. One key technique is overlapping computation and communication.
Oh, they manage that.
They use a dual micro-batch strategy. While one batch is doing, say, the MLA compute, the other is handling the MOE communication dispatching tokens, combining results. It keeps the GPUs busy.
Hiding the network latency behind compute.
Pretty much. They also mentioned disaggregating the prefill and decode steps in their production setup for better real-world throughput.
But there are still limits, especially with MOE related to the network, right?
Absolutely. The time per output token, TPSOT, is critical. For MOE, it's heavily dependent on efficiently deploying the experts and that all-to-all communication for routing tokens, expert parallelism, or EP.
How fast can that communication happen?
They did a theoretical calculation using 400 GBPs InfiniBand. Comes out to around 121 microseconds per all-to-all step.
Okay.
Factoring in their overlap strategy, they estimate a theoretical peak of maybe 67 tokens per second for V3 on that hardware, though, practical limits apply.
But then they compare it to something like the GB200 NVL72 with its massive 900 GBs bandwidth.
Right. The theoretical comms time plummets to under 7 microseconds. Suddenly you're talking potentially over 1,200 tokens per second.
Wow. Just shows how much high bandwidth scale-up interconnects matter for inference speed.
It's a potential game changer, but hardware isn't the only lever. They also use algorithmic tricks like multi-token prediction, MTP.
Yeah. Inspired by speculative decoding. How does that work?
Instead of just predicting the next token, MTP uses some lightweight extra layers to predict multiple potential next tokens in parallel.
Like drafting candidate.
Exactly. These candidates are then verified quickly. It might slightly lower raw throughput operations-wise, but it significantly cuts end-to-end latency.
And the acceptance rate was good.
Very good. 80-90% acceptance for the second token, leading to about a 1.8x speedup in actual tokens generated per second.
Nice. And helps with batching, too.
Yeah, bigger effective batch sizes mean better hardware utilization, especially for the expert parallelism part.
And that raw speed is crucial for those reasoning models, or things like reinforcement learning from human feedback.
Absolutely. PPO, DPO, they all benefit hugely from faster generation. It really drives home the need for that hardware-software synergy.
Okay, let's dig into the low precision aspect more. FP8 mixed precision training.
This is a big one. We know about FP8 for inference memory saving, but DeepSeek V3 uses it during training.
Which is still relatively uncommon for large open models, right? Even though the hardware support exists.
Right. NVIDIA's Transformer engine supports it, but this is maybe the first large open model trained this way. They had to build their own framework for MOE models.
A big engineering effort, sounds like.
For sure. Collaboration between infrastructure and algorithm teams. They use fine-grained quantization tile-wise for activations, block-wise for weights.
And they open sourced their FP8 GMM implementation, DeepGM.
Yeah, which is great for the community. But FP8 training wasn't without challenges.
What were the main hurdles?
Two main things. First, the accumulation precision in Hopper's tensor cores is limited when running FP8 ops. It accumulates in FP22, which can sometimes affect stability for huge models.
Okay, numerical precision issues.
And second, the overhead of their fine-grained approach. Dequantizing involves multiplying by scaling factors, which means moving data between tensor cores and CDA cores frequently. That adds some inefficiency.
So what do they suggest for future hardware?
Pretty clear asks. For accumulation, they want higher precision, maybe FP32, or at least configurable precision.
To balance speed and stability.
Exactly. And for the quantization overhead, they want native hardware support. Tensor cores that can handle the scaling factors directly, doing group scaling in hardware.
Like NVIDIA's microscaling in Blackwell.
Yeah, that's the kind of direction they're pointing towards. Less data movement, more efficient, low-precision math.
Makes sense. What about communication compression? They mentioned log FMT.
Right. Currently, for the EP dispatch step, they use FP8, which halves the communication volume compared to BF16. They're testing other options too.
But log FMT was their more novel idea.
Yeah, logarithmic floating point formats. The idea is mapping values to log space for potentially better compression. They encode based on min-max within a block.
Did it work well?
Validation on smaller models looks promising. Log FMT 8-bit sometimes beats standard FP8 formats.
But they didn't use it in V3. Why not?
Practical limitations. The overhead of the logexp operations for encode code, plus register pressure if fused with the all-to-all comms, meant it wasn't a net performance win on current hardware.
Ah, okay, so the hardware wasn't quite ready for it.
Pretty much. Their suggestion, again, is native hardware support units that can decompress FP8 or custom formats like log FMT efficiently.
Okay, let's pivot to the interconnect itself. They trained on H800s. What was key about that hardware?
The H800 is hopper-based, but with reduced NVLink bandwidth compared to H100 400 gigabits versus 900, that's a big difference for intranode communication.
But they compensated with lots of NICs.
Exactly. Each node had 8 400G CX7 NICs for scale-out row CE communication. So you have the significant bandwidth gap, faster NVLink within a node, slower row CE between nodes.
And that gap heavily influenced their parallelism strategy, like avoiding tensor parallelism during training.
Right. TP relies heavily on that fast internode NVLink, so with it being slower on H800, they focused elsewhere.
Like enhancing pipeline parallelism with their dual pipe approach.
Yeah, overlapping compute and MoE communication better. And really pushing expert parallelism hard, using those 8 NICs per node effectively via their DTUP library.
And that led to this node-limited routing idea?
Yes, because NVLink inside a node is roughly 4x faster than row CE between nodes, they wanted to use NVLink more.
So how does node-limited routing achieve that?
They group the MoE experts and ensure that any token only needs to be routed to experts located on, at most, 4 different nodes.
So if a token needs multiple experts on the same destination node,
it only travels over the slower row CE network once to that node. Then the faster ND-Link handles the forwarding within the node. It reduces internode traffic.
Clever way to work around the bandwidth disparity. But it sounds like managing this communication wasn't seamless. SM's getting involved.
Yeah, that's a key limitation they point out. The complexity of managing this dual bandwidth system means the GPU's compute units, the SMs, end up doing network tasks, handling messages, NVLink forwarding.
Taking cycles away from the actual AI work.
Exactly. They estimate up to 20 SMs per H800 could be busy with communication overhead during training, things like data transport reductions, memory layout changes.
So their suggestion is basically better hardware integration, convergence.
Precisely. A unified framework. They talk about dedicated coprocessors for network traffic, offloading the SM as hardware support for things like dynamic traffic deduplication for their routing scheme.
And nodding towards tech like UDC UA-Link.
Yeah. The vision is converged scale-up, scale-out communication fabric managed more efficiently by dedicated hardware with better programming models on top.
Another issue they flagged was bandwidth contention, particularly on PCIe.
Right, like transferring the KV cache from CPU memory over PCIe, while the GPU is also blasting data over ROCE for EP, the PCIe link can saturate,
causing slowdowns and latency spikes.
Yeah. So they suggest dynamic traffic prioritization on ND-Link and PCIe, being able to tag traffic EP, TP, KV cache, and give it different priority levels.
More control.
And maybe even integrating NICs directly into the I/O die to bypass PCIe contention, or using NVLink for CPU, GPU links too.
Okay, now the really large-scale network, they use a multi-plane fat tree, MPFT. What's that?
Imagine each GPU having its own NIC, and each GPU NIC connects to a separate independent network plane. So 8 GPUs per node, 8 NICs, 8 planes.
Built with InfiniBand switches.
They used 400G IB switches in their setup, yeah. The ideal MPFT vision involves multi-port NICs connecting to different planes, but appearing as one logical interface using packet spraying.
Which needs clever NICs to handle out-of-order packets.
Exactly. They mentioned Connect X8 supporting multiple planes and hope future NICs fully embrace this multi-plane idea.
What are the advantages of this MPFT architecture?
Several. It's a type of multi-rail fat tree, MRFT, so they can use existing optimizations like NCCL's PXN. It's potentially more cost-effective for large clusters than deeper fat trees.
Better traffic isolation too. Congestion stays within a plane.
That's a key benefit, plus potentially lower latency than 3-layer trees and better fault tolerance due to the multiple paths.
And how did it perform compared to a standard MRFT?
Very similarly for all-to-all communication, thanks to NCCL optimizing traffic flow, negligible latency differences in smaller tests, and critically, the training throughput for DeepSeek V3 on 2048 GPUs was basically identical between MPFT and MRFT.
So it delivers the performance while offering potential cost and robustness benefits.
Yeah, it seems like a solid design choice.
They also talked about low latency being crucial for EP, comparing InfiniBand and Row-C.
The takeaway was that InfiniBand generally offers lower latency, making it preferred for performance-critical workloads, even if it costs more or has fewer switch ports.
But they had ideas for improving Row-C.
Definitely. Specialized, low-latency Row-C switches, better routing policies than standard ECMP, which struggles with AI traffic patterns.
ECMP needs randomness that AI traffic might not have.
Exactly, leading to congestion.
Yeah.
They suggest adaptive routing and better congestion control VOQ, advanced algorithms like RTTCC, maybe even user programmable CC.
And things like IBGDA, letting the GPU talk directly to the NIC.
Yes, GPU direct async. Reduces latency by bypassing the CPU. DeepEP uses it to great effect. They want broader support for that kind of direct communication.
Okay, wrapping up the discussion section, they bring it all together and look even further ahead, summarizing the need for scale-up inference, low-precision support, converged interconnects.
Right. Then they hit broader points. First, robustness at scale.
Beyond just ECC memory.
Yeah, interconnect failures, silent data corruption. They suggest more advanced checks like checksums, better diagnostic tools for users.
And highlighting CPU bottlenecks again.
Yep. PCIe between CPU-GPU is often limiting. You need massive CPU memory bandwidth to feed PCIe 5, plus fast cores for orchestration.
Leading back to tighter CPU-GPU integration via NVLink or similar.
Makes sense. Then there's the vision of intelligent networks for AI.
What does that involve?
Things like co-packaged optics for bandwidth efficiency, lossless networks with smarter congestion control, adaptive routing becoming standard, better fault tolerance, dynamic resource allocation, maybe prioritizing inference over training traffic.
Sounds sophisticated. They also discussed memory semantic communication.
Yeah, the challenge of ordering updates across nodes. Load store is programmer-friendly but needs barriers, which add latency.
So they want hardware ordering guarantees, acquire-release semantics built in.
Exactly. Enforced by hardware without the explicit barrier overhead. They propose a mechanism called Region Acquire Release, RAR, at the receiver to manage this.
And brief mentions of in-network compute for things like EP dispatch combine and native log FMT support in the network hardware.
Right. Optimizing common communication patterns directly in the network fabric and accelerating compression-decompression for formats like log FMT.
Finally, tackling the memory bandwidth wall head-on.
The elephant in the room. Model growth outpaces HBM. So suggestions like DRAM-stacked accelerators, DRAM, right on top of the logic die.
For ultra-low latency and high bandwidth.
And even radical ideas like system on wafer for maximum density and bandwidth for future monster models.
Okay, so let's recap. DeepSeek V3 really showcases hardware-aware design. MLA for memory, MoE and FP8 for cost and efficiency, overlapping work, and MTP for speed.
And crucially, their experience highlights current hardware limits, low-precision compute constraints, interconnect bottlenecks, network inflexibility.
Their proposals for the future, better low-precision units, converged interconnects, intelligent networks, memory-centric designs, feel like a practical roadmap.
It really hammers home that hardware-software co-design isn't just nice to have, it's essential for pushing AI forward. The DeepSeek V3 work provides a valuable blueprint.
So a final thought for you, our listeners. Looking at all these hardware challenges and potential solutions, improved low precision, converged fabrics, smarter networks, memory innovations, which one do you think will be the most impactful for your work in AI? Where do you see the biggest bottleneck relief coming from?
Definitely something to ponder. We strongly recommend checking out the paper itself and the open source bits like DeepEP and DeepGM. Lots to learn there.
Absolutely. Thanks for tuning in to AI Paper Podcast today.